In the last lecture, we have discussed various types of the sets. Today, we will discuss two more sets which are very important sets. One is the derived sets and other one is the dense set. The derived set basically is the collection of all the limits points of the sets, and dense sets is basically a set whose closure coincide with the space. Suppose a set A is a subset of X, then A will be dense if its closure will be the X itself. That is, if I picked up a point, any point element from X and draw the neighborhood, then one can always find at least one point or some few more points, you can say, of the set E. So, the element of X and element of the set X are very close to each other. The total length of the Cantor set is 0, that is measure of the set is 0. Is clear? Now, next the last one which we want to show is the D part. The Cantor set is uncountable. Is uncountable. Okay. As we seen, the Cantor set contains all of the endpoints, of the removed open interval intervals, and these points are of the form 2 to the power k over 3 to the power k n of 3 to the power n, where k is 0, 1, 2 up to say n for each n. The collection of these points is the Cantor set. We wanted to show this Cantor set is uncountable. Okay. So, these are infinite. First thing is the Cantor set is an infinite set, because there are so many points are available. So, it is an infinite set. Clearly, Cantor set is an infinite set. Okay. Infinite set. Now, let us take, if we take any point x belongs to the interval 0 to 1, then we can, since each point x belongs to a can be represented internally, that is with the base 3, and its expansion will be x equal to sigma n is 1 to infinity n over 3 to the power n, where each n is either 0 or 1 or 2. Any point in the closed interval 0, 1, a real number, we can express it in the a decimal expansion, in that expansion, in the ternary expansion with the base 3 h1. So, we can write this form as a 1 by 3, a 2 by 3 square, a 3, and the where a 1, a 2, a n may be 0, 1 or 2. Okay. This will be the. Now, if x lies in one of the, it is observed, it is also observed that if x lies in one of the removed open intervals, in one of the removed, then then at least then a n's will be 1 for some n. For example, suppose I take the interval, the each point, suppose I take for example, each point in the interval 1/3 2/3. This is the doped interval has first term a 1 is 1. Similarly, the end points of the removed interval similarly. So, this is true for each x. It is observed that you can write it that each x that lies in one of the open interval has a n's to be 1 for some n. This is true. Now, in the interval say end points, further the end points of the removed interval say 1/3 2/3 have two possible ternary expansion, have two possible ternary expansion, one having no ones and set other may be some ones or two. For example, if I take this 1/3, the expansion of the 1/3 internally will be 0.1 0 0 0 0 third. If I take the same one, then we can also put it in this form 0 2 2 2. If you approximate, you will get 1. So, one of these expansion will involve ones and others may not have a ones also. Okay. So, at least one will have no n's will not be 1. Okay. So, this one. So, what we want is now we choose that expansion. If we choose, and these are the endpoints are in the Cantor sets. So, now we choose the expansion, of the points of Cantor set x, expansion of the point say x of Cantor set in such a way such that its ternary expansions has no ones. Okay. That is we wanted to have it, no ones. That is, the ternary expansion will involve n, which may be either 0 or 2 for all n belongs to n in the ternary expansion of each point of points x belongs to Cantor set. This we are assuming. Okay. Now, define a mapping psi from the Cantor set F to say closed interval 0 1 as follows. If I take a point x whose ternary expansion will be 1 to infinity a n 3 to the power n. This is the ternary expansion, and what we are doing is we are taking the image of this under psi as the point whose binary representation is this a n by 2 divided by 2 to the power n. That is for each x belongs to a. That is what we are doing is, that is the image of this psi a 1, a 2, a n and so on in ternary expansion and so on. This is a ternary expansion of this point in ternary expansion is nothing but the expansion of the same point in binary mode b 1, b 2, b n etcetera in binary 2, where v n's will be a n by 2 for all n belongs to n, for all n belongs to n. So, this is our means each point I am picking up from here, writing down is ternary expansion, and then image of this we are taking the image as a binary expansion of the same points, okay? Binary expansion for this. Okay. So, what we are doing, this binary expansion will also be a point in 0 1. So, each point which is in F will have a point in the 0 1 which is in 0 1. So, this psi is a onto mapping, okay, from F to 0 1. Now, let us suppose the F is countable. Suppose F is countable. This Cantor set F is countable. So, if it is countable, then there exists a mapping say phi from F to n or n to F, 1 to 1 correspondence with the which is 1 1 correspondence on to 1 1 on to 1 1 mapping correspondence for this. So, there exists F psi which is 1 1 from this to this surjection mapping. Okay, F is countable. So, there is surjection of 1 1 onto. Okay, onto. So, if we combine this thing, it means when we combine this, then what you are getting is that the composite mapping, composition of phi and psi, this will a mapping which brings the n to 0 1 n to 0 1 as surjection. This is a surjection mapping onto mapping. So, if we assume F to be countable, then basically this implies that this is F and this are having the surjection. There is a mapping from F to 1 which is surjection 1 1 onto a onto mapping. So, once it is surjection, then since we have assumed F to be countable, so this implies that 0 1 is a countable set, as we assumed F is countable. F is countable. This is our assumption, but 0 1 is uncountable set. What 0 1 set of all real number in between the 0 1, that is continuum, is an uncountable set which we have already shown. So, our assumption is wrong. Therefore, this implies that Cantor set is uncountable, and that is proved the results. Okay. So, this is what we. Now, another examples which we want to show, define the derived sets problem. Define derived set, define derived set, and so that the rational numbers in 0 1 derived sets, and so that the rational numbers in the interval 0 1 is a set of second species, So, let us see first what is the derived set and what is the species we mean. Derived set, if the set S is infinite set, then what we do is we can find out the limits of this. We can find out the limit of this set. A infinite set may have a many limit point or may not have a limit point also, depending on the set. So, if the set is infinite set, there is a possibility of having the limit points. So, we define the derived set as follows. Okay. The set formed the set formed by the limiting points by the limit points of the set S of the given infinite set is known as the derived set, because finite set does not have any limit point, that we have already seen. So, that is why we are taking derived sets, derived set. So, suppose I take the set S which having say point half, minus 2/3, 3/4, minus 4/5 and so on. Now, the derived set n is denoted by S dash by S dash. So, let S be the, I will write like, let S be an infinite set, be an infinite set of points. Then the set formed by the limit points of the given infinite set S is known as the derived set and denoted by S dash. So, for example, if we take this one, then what are the derived set? 1/2, 3/4 etcetera, the limit point will be 1, and minus 2/3 minus limit point will be minus 1. So, this is the derived set having this point. Now, in case if derived set S is itself an infinite set, then there is a possibility of having limit points of S dash, and then the collection of these limit points, the collection of the limit points of S dash is denoted by S double dash and is called and is known as the second derivative, second derived set of S. Continue this like this. So, suppose if we continue this, suppose we have, after proceeding n, we have the S n comes out to be finite. So, proceeding this way, continue. If S dash, this is the first derived set, S double dash is the second derived set, S n is the nth derived set of S. These are the derived sets of S, and if S n is having finite number of terms, and if S n, the nth derived set has finite number of points only, then we cannot go further. That is, we are unable to get the limit point of S n, and then we stop it here. Then we say that set S, the set S, if it is the S is that set S contains in next step, and it is a derived set. S is of order n and is of first category, that is first species. On the other hand, if S n is again infinite set for large n, for large n greater than, then S is said to be, large n means for every n, you can say, then S is said to be, of second species. So, this is the way. So, for example, the set of rational number, if is the set of rational numbers in the interval 0 1, it is of second species. Why? Because the set of limit point of this is the set of rational in the all rationals in the interval 0 1, then set of all irrational will also be the limit point of this, and basically this is nothing but the interval 0 1 itself. So, continue this, we get every times the derived set is comes out to be the set itself, that is this possible to get the limit point of this. So, it is of second category. Okay. So, that is what we want. Now, then we next problems. So, that problem which we have defined the range, so the rational number is of second species. Okay. Then define the dense in itself, everywhere dense set, and dense set. With examples. So, let us see the solution for it. What is our definition for the dense in itself? So, let us see the solution. We define the dense in itself a set S is said to be dense in itself if every point of S is a limit point of S, If every point of S is a limit point of S, then we say the set is dense. So, in such a case, so if S is a dense set itself, then it is subset, then so S will always be subset of S dash, because every point of S is the limit point. So, it is the S dash will contain all the point of S. Okay. S dash. Thus, for example, if we take the set S as a closed set S is the closed set, closed intervals, all may be open intervals, all may be open intervals. These are all dense in itself, Okay. Then set of rational number, irrational number, and the set of irrational number, rational number, set of rational numbers in any interval is dense in itself, set of irrational numbers in any interval is dense in itself, and like this. Now, we define the everywhere dense set. A set S is said to be everywhere dense if every point of the interval I in which S is contained is a limiting point of S. Means what a set is said to be dense, everywhere dense, if the interval in which S is lies, every point of that interval in which S lies must be a limit point of S. For example, if we take this closed set, then for example, if we take the closed sets or closed interval, S is the closed interval 0 1, then this is everywhere dense, because the interval in which it lies will be that set closed interval. But if we take this one dense, but this is everywhere dense, okay, everywhere dense, because the interval is. But if we take the set S as the union of these interval 0 1 and then 2 3, if this set, if I take collection of all points in between this, then this is dense in itself, because dense in itself means every point of this is a limit point, but is not everywhere dense. Why is not everywhere dense set? Because a interval 0 1 0 3 does not contain the point in between 1 and 2. So, it is not every point, okay, dense. Then a set is said to be dense set, and lastly dense, we say a set S is said to be dense, if between any 2 point, between any 2 points of S, there is at least one other point of S, then it is a dense. For example, if we take the interval 2 3, this is our S, then this is dense set, because between any 2 points there is a point of the interval. But if we take this set, say 0 1 comma 2 3, this collection S is not dense, because between any 2 points we do not get one between 1 and 2, the point which is available here. So, that is what is dense. Okay. A set is nowhere dense set, a set S is said to be nowhere dense or non-dense if there is no interval in which S is dense. For example, if we take the set of rational numbers 1, 1 by 2, 1 by 3, this collection is nowhere dense, because we cannot get an interval in between these whichever. Thank you very much. Thanks.